We have studied so far that EMF is induced in well-defined paths like closed loops when they are subjected to changing magnetic flux. A thought that arises is that whether current can be induced in bulk pieces of metal. If yes, then what will be the implication wherever metal is used and there is changing magnetic field associated with it? We will be talking about this in the module. We will also study the concept of induction in a single long solenoid and induction when there are two long solenoids. When bulk pieces of conductors are subjected to changing magnetic flux, then induced currents are produced in them. The current which are induced in bulk pieces of conductor when the magnetic flux linked with them changes are called eddy currents. Their flow patterns resemble swirling eddies in water. Therefore, these currents are called eddy currents. This effect was discovered by physicist Foucault. Therefore, these currents are also called Foucault currents. Take a look at the diagram to know this better. The magnitude of eddy currents is given by I is equal to EMF induced EMF E upon R. And we know that E is equal to minus d phi by dt. Therefore, I is equal to minus d phi by dt upon R. The direction of eddy current is given by Lenz's law or the Fleming's right-hand rule. Here also the Lenz's law is at work. Changing magnetic flux produces eddy currents, which will be induced in such a way so as to oppose the very cause of its production. This results in an often undesirable conversion of mechanical energy into internal energy. An example of eddy currents is the following pendulum with a conducting sheet in which eddy currents are induced such that the pendulum slows down every time it passes through the magnetic field. Eddy currents can produce significant drag called magnetic damping on the motion involved. Let us take a look at the pendulum first. Let me explain the damping. As the sheet enters the field from the left, the flux linked with the sheet increases and the eddy currents are developed in the anti-clockwise direction. This sheet experiences a force in the left direction, which tends to slow it down. Once the copper sheet is inside the field, the flux associated with it is constant. Now, as it moves out of the field from the right direction, the flux decreases. Eddy currents are induced in the clockwise direction and then the sheet experiences a force in the left direction which again slows it down. Thus, eddy currents produce a dampening effect on the motion of the sheet and finally brings it to a stop. You can take a look at the diagram. The electromagnetic braking finds its application in magnetic braking of trains. Strong electromagnets are situated above the rails in electrically powered trains. When the electromagnets are activated, the eddy currents induced in the rail oppose the motion of the train. As there are no mechanical linkage, the braking effect is smooth. Certain galvanometers have a fixed core made of non-magnetic metallic material. When the coil oscillates, eddy currents generated in the core oppose the motion and bring the coil to rest quickly. Another application is that of induction furnace. Induction furnace can be used to produce high temperatures and can be utilized to prepare alloys by melting the constituent metals. A high frequency alternating current is passed through a coil which surrounds the metal to be melted. The eddy currents generated in the metals produce high temperature sufficient to melt it. Eddy currents generate resistive losses that transform some form of energy such as kinetic energy into heat. Induction furnace utilizes this heat, but this joule heating reduces efficiency of iron core transformers and electric motors and other devices that use changing magnetic fields. In order to increase the efficiency of these devices, eddy currents should be minimized. This can be done by selecting core materials that have low electrical conductivity, like ferrites, or by using thin sheets of magnetic material known as laminations. Electrons cannot cross the insulating gap between the laminations and so are unable to circulate on wide arcs. This reduces the strength of the eddy currents in these devices. Take a look at the picture. Let us now discuss the concept of induction. An electric current can be induced in a coil by flux change produced by the another coil in its vicinity, or by the flux change produced by the same coil. The property of a solenoid by virtue of which it opposes any change in the strength of the current flowing through it by inducing an EMF upon itself is called self-induction. The question is, why do the solenoid behave like that? Let us take a look at the diagram and understand it better. As soon as the key in the circuit is pressed, the current through the coil increases. This changes the flux linked with the coil, and again the coil doesn't like it. It induces a EMF upon itself so as to oppose this change in the flux. This EMF will be induced in such a direction that it will try to decrease the current flowing through it. If I is the current flowing through the coil, then the flux linked with the coil is given by phi, which will be proportional to I. Or, removing the proportionality sign, we can say phi is equal to L into I, where L is the constant of proportionality and is called the coefficient of self-induction. The value of L depends on the following: number of turns, area of cross section of the coil, nature of the material of the core, and if I is equal to 1, then L becomes equal to phi. Therefore, we can define coefficient of self-induction as the amount of magnetic flux linked with the coil when the unit current flows through the coil. Now, the EMF induced by the coil is given by E is equal to minus d phi by dt. Phi, as we already know, is equal to L into I. Therefore, EMF E is equal to minus d over dt of Li equal to minus L di by dt. If this di by dt is equal to 1, then the induced EMF E is equal to minus L. Hence, coefficient of self-induction can also be defined as EMF induced in the coil when rate of change of the current through the coil is unity. The SI unit of self-induction is Henry, represented by capital H. Now, we can say that L is equal to minus E upon di by dt. So, 1 Henry will be equal to 1 volt upon 1 ampere per second, or 1 Henry is equal to 1 volt second per ampere. Let us find out the self-induction of a long solenoid. A solenoid is a tightly packed helical coil. A long solenoid is one whose length is very large compared to the radius of cross section. We know that for a solenoid, magnetic flux linked with the coil is given by phi equal to L into I. Also, magnetic flux is defined as N into B into A, where N is the total number of the turns and B is the magnetic field associated with the coil and A is the area of cross section. So, L into I is equal to NBA. Now, for a solenoid, we already know that B is equal to mu naught Ni, where here we have small n, which is the number of turns per unit length. So, L into I becomes equal to N, and in place of B we write mu naught Ni by L. Here this N is capital N, which is the total number of turns. So, capital N upon L becomes our small n, which is the number of turns per unit length. This whole into A. Now, L becomes equal to mu naught capital N square A upon L. If the core of the solenoid is made of any other magnetic material, then mu, the magnetic permeability through that material, becomes equal to mu naught times mu r, where mu r is the relative permeability. So, L is equal to mu times N square A by L, or L becomes equal to mu naught mu r N square A by L. If small n is the number of turns per unit length, as I already told you, so small n becomes equal to capital N by L. And multiplying and dividing by L, we get L is equal to mu naught mu r N square, small n square this time, A into L, where small n is capital N by L. Now, the energy required to build up a current through a solenoid. The self-induced EMF is also called the back EMF, as it opposes any change in the current in the circuit. That means that as the current is trying to grow through the circuit, the back EMF is trying to pull it back. So, there has to be physically the self-inductance plays a part of inertia, or it plays a role of inertia. When a current flows through the solenoid, work has to be done against the back EMF. This work done is stored as magnetic potential energy. Let us try and calculate the same. For the current I at an instant in the circuit, the rate of work done is dW by dt, which will be equal to E into I. As we already know, power is V into I. So, replacing E equal to L di by dt, we get power is equal to dW by dt, which is equal to L di by dt into I. As dt cuts out on both the sides, we have dW is equal to Li di. The total amount of work done in establishing the current I is given by W equal to integral over dW, which will be equal to L integral going from 0 to I di. So, that gives us the total work done in building up the current by the solenoid. So, work done is equal to half Li square. This expression reminds us of half mv square for the mechanical kinetic energy of a particle of mass m, and shows that L is analogous to m. That is, L is electrical inertia and opposes growth and decay of current in the circuit. For practical purposes, we can combine the solenoids in series as well as in parallel. Let us see how. You can see these coils are connected in series. When any number of coils are connected in series, same amount of current flows through them and the potential divides across them. Mathematically, E is equal to E1 plus E2 plus E3 and so on till En, which will be equal to Ls, which is the inductor across the whole series of inductance, Ls into di by dt will be equal to L1 di by dt plus L2 di by dt and so on till Ln di by dt. So, all di by dt is cut on both the sides and we get Ls equal to L1 plus L2 and so on till Ln. Therefore, combined inductance of coils connected in series is equal to sum of inductances of individual coils. In series, the total inductance increases. Now, coils connected in parallel. When coils are connected in parallel, then the potential remain the same and the current gets divided. Hence, so IP through all the parallel combination of solenoids is equal to I1 plus I2 and so on till IN. dIP by dt will be equal to di1 by dt plus di2 by dt and so on till din by dt. As the potential is same across all, we get E by LP is equal to E by L1 plus E by L2 and so on till E by Ln. So, we get 1 upon Lp is equal to 1 upon L1 plus 1 upon L2 and so on till 1 upon Ln. So, in parallel connection, the reciprocal of combined inductance of any number of coils is equal to sum of reciprocal of inductance of individual coils. Thus, in parallel combination, the total inductance is less than the minimum value of the inductance of any coil. Let us consider the case in which electric current can be induced in a coil by flux change produced by the another coil in its vicinity. This is called mutual inductance. You can see in the diagram that mutual induction is a phenomena in which changing current in coil 1 produces a changing magnetic flux of coil 2 placed in its field. This induces an EMF in coil 2. This EMF is induced in a way so as to oppose the cause of its production. The induced current will be induced in a direction which will oppose the increasing magnetic flux associated with coil 2. Take a look at the model. In this, coil 1 current is passed and coil 2 is placed in the vicinity of the first. The AC current is varying the magnetic flux associated with coil 2. This induces an EMF in the coil 2. This is mutual induction. Let us find out the coefficient of mutual induction. It is found that the flux phi is proportional to I, or phi is equal to m into I. M is the constant of proportionality called the coefficient of mutual induction, which is numerically equal to magnetic flux linked with the coil when unit current flows through the neighboring coil. So, phi is equal to m when I is equal to 1. The induced EMF in the neighboring coil is given by E is equal to minus d phi by dt, which will be equal to minus d over dt of m into I, equal to minus m di by dt. If di by dt is equal to 1, then E is equal to minus m. Hence, coefficient of mutual induction can also be defined as EMF induced in one coil when rate of change of current through the other is unity. SI unit of mutual induction is Henry, represented by capital H. Coefficient of mutual induction is said to be 1 Henry when the rate of change of current through one coil is 1 ampere per second and this induces an EMF of 1 volt in the other coil. Factors on which coefficient of mutual induction depends are geometry of the two coils, that is the size, shape, number of turns, nature of the material of the coils which are made up of, nature of the material on which the two coils are wounded on, distance between the coils, relative orientation of the two coils. Let us study in details the orientation when the two coils are coaxial. You can see in the model, coil 2 is connected to the AC mains and coil 1 is connected to the LED. Coil 1 has no source of power supply. As we switch on the supply and bring coil 1 in the vicinity of coil 2, mutual induction takes place and the LED glows. And it glows, you can see this. We want to study the orientation where coil 1 is coaxial with coil 2 as seen here. You can see in the diagram as well. The two coils are coaxial with each other. The two coils are long solenoids, each of length L. We denote the radius of the inner solenoid S1 by R1 and the number of turns per unit length by N1. The corresponding quantities for the outer solenoid S2 are R2 and N2 respectively. Let capital N1 and capital N2 be the total number of turns of the coil S1 and S2 respectively. When the current I2 is set up through S2, it in turn set up a magnetic flux through S1. Let us denote this flux by phi1. Now each turn of S1 will be associated with the same flux phi1. Therefore, flux linkage is given by N1 phi1. This will be equal to N1 phi1 equal to M12 I2. So, changing current I2 is responsible for flux linkage of N1 phi1 and 2 are proportional through M12. The coefficient of mutual inductance of solenoid 1 with respect to solenoid 2. Let us calculate M12. N1 phi1 is equal to N1 B2 A1. B2 comes because 1 is placed in the magnetic field of 2. So, we have N1 phi1 equal to N1L, here small n1 is number of turns per unit length, mu naught N2 I2 that is B2 and pi R1 square that is the area of cross section A1, which will be equal to mu naught N1 N2 pi R1 square L I2. Comparing equation 1 and 2, we get M12 is equal to mu naught N1 N2 pi R1 square L. We have neglected the edge effects and considered the magnetic field to be uniform throughout the length and width of the solenoid S2. This is a good approximation, keeping in mind that the solenoid is long, implying L is much greater than R2. Now, let us see what happens when current through solenoid 1 flows and due to it the flux associated with the 2 changes. The situation is somewhat similar but not exactly similar, and a flux linkage with the coil 2 is given by N2 phi 2 equal to M21 I1, where M21 is the mutual inductance of 2 with respect to 1. Now, this flux linkage can also be given by N2 phi 2 equal to N2 B2 A1, because phi is B into A. But one thing that strikes is why I have not written phi 2 as B2 into A2. Instead, I have written phi 2 as B2 into A1. The reason is that it is a long solenoid, therefore, no field is there outside S1. So, effective area of cross section where the flux will be limited to A1. So, N2 phi 2 is equal to N2 B1 A1, which will be equal to N2L into mu naught N1 I1 into pi R1 square equal to mu naught N1 N2 pi R1 square L I1. Comparing this equation with the previous equation that we got, that is equation 4, we see M21 is equal to mu naught N1 N2 pi R1 square L. From equation 3 and 6, we can say that M21 is equal to M12 is equal to M. If inner solenoid is smaller than the outer solenoid, then we can find the linkage N1 easily, as inner solenoid is in the uniform magnetic field of the outer solenoid. Finding M12 is easy, but when we try to find M21, then it is difficult, as now the outer coil is in non-uniform field of the inner solenoid. In this situation, the relation M21 equal to M12 equal to M is very useful. If the medium of relative permeability mu R had been present, the mutual inductance would be M equal to mu R mu naught N1 N2 pi R1 square into L. It is also important to know that mutual inductance of a pair of coils, solenoids, etc. depends on their separation as well as their relative orientation. After learning about the mutual inductance, we'll be doing its application in the transformers in the upcoming modules. Thank you.